Hello students! Today we're going to be talking about statistics relevant to psychology. So if you've taken a stats class before, you're probably going to know everything that we're discussing here today, because we're really going to focus on the concepts behind the statistics relevant to psychology. So things that you'll see a lot, we're going to just talk about what the terms mean, give some examples of them. We're not going to actually go into any of the math today, except maybe to mention like what an average is, like how to calculate that. But we're not actually going to talk about how to calculate these statistics or anything about the math. Also, for at least the 2010 class that I'm originally making this for, it won't be on your exam. The math won't be on the exam. So you're not going to be required to calculate any of these statistics, but understanding the concepts will be really important. So as you're reading psychology papers, as we're discussing studies in the class, knowing what a mean is or the difference between means, those are things that'll come up, and the concepts there, that will be useful for you. So reading your intros and your discussions of your papers, it'll be really useful to know some of the basic concepts of statistics, even though for most of the undergraduate classes I teach, knowing the results and discussion, or the methods and results sections where most of the stats are actually going to be, and they're talking about how they calculated it and what they calculated. Most of my classes in undergraduate level aren't going to focus on that, but knowing the concepts will really help you understand the intros and discussions of these papers and the ones that we use in this class as examples. So let's talk about some of those concepts. We will start with population. A population is essentially everybody in an entire population. So the population of the United States, the population of the world. You can have smaller populations too. So you can talk about the population of the employees of Amazon. You can talk about the population of students at Salt Lake Community College. So that can all be in the entirety of the group that you're looking at is the population. So all humans is all humans. That's the population of humans. So everybody on Earth, and then also in the International Space Station. So that's the population of humans. So you could think about a stat relevant to that, the ethnicity of everyone in the population of the United States. What are the percentages of ethnicity across the population in the United States? So a sample is usually what we're talking about in any given study. So we're talking about the sample of that population in your study. So in your study, what segment of this population are you looking at? That is your sample. So if I am doing a study of the entire population of Salt Lake Community College, I might take a sample. My sample might be everybody in classes on Wednesday. And that's not everybody in the school. It's probably a large chunk of them, but that's just a sample. Everybody in classes on Wednesday, that's the sample I'm sampling. So you could also take a look at the ethnicity of 500 people that you've randomly selected across the USA who have volunteered for your study. So the population of the USA and all their ethnicities, that's everybody in the whole country, versus the sample, the ethnicity of those 500 people. And that might give you some ideas about the population. So here's a couple different graphs that we might use to demonstrate some of this data. So you've probably seen pie charts in the past. This is ethnicity data from the US in 2019. So one way to display this data is like this in a pie chart. You can also do a bar graph, something like this. So here it's comparing in 2010 to 2050. It's projecting what the population will look like ethnicity-wise in the entire US. And then this is another way. This is more similar to a histogram here. So we've got these different bars meaning different things, and then you've got the percentage here. So a couple different ways to visually demonstrate some of this data. So we've got pie charts, bar charts. Histogram is a special kind of bar chart that just shows the data in a different way. So this is an example of a histogram looking at the population of height in the US. So we've got, it's broken up by sex here. So we've got men and women. And so with this, we also see this little curved line. So this might look similar or look familiar to you. This might be called a bell curve or a normal curve. This is the normal distribution of these variables. So we've got our data for men and women here. And so there's some people that are this tall, some people that are this tall, some people that are this tall. It's overlapping so you can't see, but there's probably some people this tall in the men group as well. And you can see this distribution is kind of shorter and wider. That means the data has more variance. There's more variability in that. There's more people that are higher and lower than in the women group. So here you can also see this bar and some of these bars go beyond that normal distribution. And that's essentially because the normal distribution is calculated off of the average of these groups. So the average for the women group is right here. But you can see obviously there's data outside that average. There's people shorter and higher than average. And so with this distribution is a little more squished. There's less variability around that mean, around that average, than there is in this men group. So again, we have a histogram and we have a normal distribution. That's another way to graph this. Then here we have those same normal distributions, but we've removed the histograms. So depending on how you want to look at the data, using graphs in different ways can help you focus on different things. So here you can clearly see some things marked. So you've got the average, which is the mean. So the mean of this group and this group. And then you've got people that in the women group are a little bit tall. So this would probably be about a standard deviation up. So a little bit above average, but still within that first range. Even taller, so a little bit more above average. And then over here it says extremely tall. Only about 99% of people fall past this star. So it would be someone who's on the street, you would see them and you'd say, oh, you're unusually tall. You'd also have one of those stars on the other side of the line too, where it's 99% of people are taller than these people. So this is one way that we can look at data. So here we've got, again, pie charts, we've got bar graphs, histograms. This histogram has the normal distribution, and this is just the normal distribution by itself based off of your sample. So again, we've sampled maybe 500 people across the US, got their heights, split them up by sex, and compared those. So what might you find in your sample? So most of these graphs were of the entire US population, but what might you find in your sample? So let's say we took a sample of ethnicities in Salt Lake City. Does Salt Lake City's ethnicities look different than the rest of the countries? Well, yeah, it does. There are a lot of differences here. So the group that's white is bigger in Salt Lake City than the rest of the country on average. And then it's kind of hard to tell from the colors here. The next biggest here is labeled Hispanic. And so you can see the size difference there. And then it looks like, I think this one is, this is partially the image quality, partially the screen I'm looking at, but I think this sliver here is black. So you can see how different that is. So the sample here, if we took our whole sample from Salt Lake City, we might not be getting a good representative picture of the USA. So if that's the population we wanted to make inferences of or make claims about, if our sample only comes from Salt Lake City, we might not be able to make claims if, say, ethnicity is a critical piece of our variables that we're looking at, because the ethnicity breakdown is so much different than we see population-wide in the US. So sample is useful because that's where we're getting our data. It's the actual people that we're studying, we're surveying, we're measuring, and usually we're trying to make claims about a population, and the better our sample represents the population, the better that would be. So instead of taking maybe 500 people from Salt Lake, maybe we take 100 people from Salt Lake, 100 people from somewhere on the East Coast, 100 people from somewhere on the West Coast, 100 people from the Midwest, and then another assortment of 100 people. That would probably give us a closer representation of the actual population. So population and sample are two terms I hope you get clear in as we continue talking about things. So I couldn't actually find data on the height of people in Salt Lake City, but do you think that it would differ from the population of the US dramatically? So why or why not? So maybe write down in your notes. I couldn't really think of any particular reason we would find any significant height differences in Salt Lake City versus the population of the US. So I would imagine our sample here in Salt Lake, we're talking about height, would probably look pretty similar to the population of the US. I can't really think of any state or city or place where there would be a lot shorter people or a lot taller people. So I'm guessing height is one that we'd probably find a pretty similar breakdown. So what inferential statistics means, you might have gathered it already when I've mentioned inferring a few times. We take data from our samples. So that's all the data we have. We have our sample, and then we make generalizations about the population. So if we want to know about Salt Lake Community College, we ask questions of a sample of Salt Lake Community College students, and then we try to make inferences. We infer that might be how the population acts, behaves, feels about something. If we ask everybody at Salt Lake Community College what their political party is, or if they have no political party, where they fall on the political compass, if we ask enough people, we probably get enough variance there that we could say, hey, we can probably generalize or assume that the rest of the population of the school probably falls within these ranges. But if we only ask a sample of 10 people, it's probably not enough people to ask to make good generalizations or to infer things. So if your sample is from data from about 500 people across the US, you can probably make some inferences about the population of the United States. If it's 50 people, you probably can't. That's too few people, not enough differences. So let's say you have a correlation between well-being and education in your sample. You may be able to infer that there is a relationship between well-being and education in the population. So what might cause you to not be able to infer something about the population? It's not a trick question. I've already kind of answered this a few times. So if your sample is too small or too different than the population, you won't be able to infer anything meaningful or accurate about your population. So if our sample is all really tall people, then we can't infer things about the height of the US, right? Because we got just tall people. Or if we're only taking data on ethnicity from people in Salt Lake City, well, we're going to get a lot more white people in that sample and a lot fewer black people in that sample than if we took samples from across the United States. So if our research question was relevant to ethnicity, then that might be a problem, right? We wouldn't want just a sample from Salt Lake City. Now, if it was a variable that ethnicity didn't matter to, then it might be one of those individual differences that just doesn't matter in the relationships that we're looking at. So if we're looking at how people process memories, the sample doesn't matter that much. Pretty much people's neurology tends to work similarly. There's obviously neurodivergence, but with that, brain's processing of memories tends to do the same thing. The memories are stored in the same way. Now, how are they retrieved and activated or primed? There's where we get into some more neurodivergence. But the actual storage of the memories tends to be pretty similar across people. So depending on what variable you're looking at, it may or may not matter how different or similar your population is. That's one reason some of the MRI studies you might see have so little of samples, because maybe what they're looking at, the differences between people, it doesn't matter if they have 20 or 200 or 2,000 or 2 million, the brains are going to be working pretty similarly. Also, it's really expensive to do MRIs, so that's another reason they tend to have very small samples. So, descriptive statistics. This is just a term to say that we're describing our sample. They're stats we use to describe the sample, and I've already mentioned quite a few of them today. So, demographic variables describe the sample. So age, gender, ethnicity, socioeconomic status, these are all demographic variables that we use to describe the people that are in our sample. And that's relevant because when you're looking at a study and this population all came from a specific demographic, a specific gender, a specific age, if you only had people that were between 18 and 25, and then you have another study that or you want to apply the same treatment to people that are 50 and older, depending on what it is, it may or may not be relevant for the 50 and older group. So that's why we include descriptive statistics, to let other researchers know this was a general description of the people in my study. So also, using central limit measures is a kind of descriptive statistic. It describes what our sample's results were. So central limit measures basically describes any given variable in the sample in different ways that measure a central kind of measure. So what is the central measure we've already talked about here? The average, the mean. So the mean is one example of the central limit, and also it helps us know, central limit measures tell us about the spread of the data. How variable is it? Is there lots of people way out here, or is everybody really squished close together to the same numbers? So mean, median, mode, these are all trying to get at a middle number. Standard deviation, skew and kurtosis, and outliers are all referring to spreads of data. So let's go over these in individual. So mean, hopefully you know this one already. This is the average. So the average of heights for men looks like it's about, and this was the US population, looks like about 71 inches. For women, it looks like it's right at 85 inches. So that's the average. So if you take all the scores, divide them by the number of people, that's your average. So you could have an average score on intended heroic behavior. You could have an average score on intended pro-social behavior. You could have an average score on a depression measure. You could have an average score on happiness. A lot of surveys that are used in psychology use means as their score. So it's just your average for one group versus another group, your treatment group versus your control group. So if this was a treatment group, I'm assuming in this case you're wanting your treatment to move them in some way. So your treatment group versus your control group, their mean is here versus this mean is here. So another central limit measure is median. It's the middle number in the spread. So women here have a different middle number than men because men's spread is further. So in this case, the median is probably going to be pretty similar to the mean in height in this specific case. In some cases, median might be a better measure when the data is skewed. So if the data is really skewed one way or the other way, so if this data is over here or over here, knowing the very middle of all the data might be really useful. So you might hear the median income in the US. That takes the middle number of income. It's a little better than average because it's a little better number to get a sense of how much money people are making in the US, because we have people making billions and billions of dollars, and so that really pulls the average towards those dramatically high numbers. So mode is the most common number. So depending on what you're looking at, you might want the mean, you might want the median, you might want the mode to describe the middle of your data. Usually mean is used, but depending on what you're doing, you might want median or mode. So standard deviation measures how far the data is spread around the mean. So just how far out is it spread? The standard deviation for the men group here would be bigger because the spread is further than the women's group. The women's group is more squished, so the data is not spread out as far as for the men's group. And in this case, for heights, it's saying that there's not as much variance in the height of women in this, I guess this was the US population versus the men's population. So if it's wide or is it narrow, here again, men's heights is wider. So skew and kurtosis basically looks at, does this data fall well enough in the normal distribution? If you tied a normal distribution line to this based on the mean and standard deviation, does the data actually make sense to qualify as normal? And that's a statistic term for, is it pretty close to a normal distribution? This here is very close to normal distribution. You can see there's some of these histogram points poking out over that normal distribution arc. But this is very, very close. This is very close to normal distribution. You generally find that with things like heights and weights of humans. So these heights look like they're very close to that bell curve. So again, normal distribution, bell curve, yeah. But if we look at something like this, is this skewed too far to be considered a normal distribution. This one probably would not be a normal distribution. So this graph is really good for thinking about median. So the average number here, when you have, so here is $206,000 a year for household income. Now, $1 million would be further than my mouse can go over here. And then billions of dollars would be literally, if I would have to have more money to get more screens to have the graph go that far that way. So those really high numbers are called outliers. They pull things over, they pull the mean over. Because if you have 10 people making $10 and then one person making $1 million, well, your average score is going to be quite a bit higher to that million because it's such a dramatically higher number. So sometimes this will happen in a data set where an outlier is in there accidentally. Let's say that someone didn't respond, but you've told your statistics software to score their non-response as a 0. Well, that might calculate. The computer doesn't know that. It just knows there's a 0 here. I'm going to calculate that. So it's good to look at outliers when you're looking at your statistics to see, is this a real person's data or did something get messed up? So also, is this outlier relevant? Obviously, we're talking about people making billions and billions of dollars. That's very relevant. But it just depends on your research question, right? If you only want to know about people making less than $206,000 a year, you can cut out all those outliers. You can literally delete them from your data if it's relevant to your research question. So this is pretty skewed. That's why using the middle number would be good, because the mean would probably be higher than the middle number. So again, mean, average, median, middle number, mode, most common number, standard deviation. How spread around the mean is it? Skew and kurtosis, is it about normally distributed? And then outliers, is there anyone pulling the data one way or another? And then is that real data or is it not real data? So let's look at some psych measures and take a look at these things. So this is actually from one of my dissertation studies. One of the measures I used with the people in my study was an intention or a prosocial behavior intention scale. So the higher the score, the scale went from 1 to 7. So 1 over here, 2, 3, 4, 5, 6, 7. So the higher your score, this is an average score for any individual. The scale was 4 questions. So basically averaged those 4 questions total, and most people actually scored a 7 on all 4 questions. So you can see, does this look very normal? Normally distributed? Could we do a nice bell curve on this? Not really. It's pretty skewed. The mean was very high, 6 point something, because there are so many people scoring 7. The skew and kurtosis, it's interesting statistically because running the skew and kurtosis, it said that this was still okay statistically to use as a normal distribution. But I mean, that's a problem I'll discuss with advisors looking over my PhD work. But I do find it interesting that much of a skew was still counted okay as being normally distributed enough. So compare this to the intended heroic behavior scale. So that was a big part of my dissertation, was creating this measure, and I really wanted it to be able to distinguish people who really would potentially act heroically and people who would not. So it was 8 questions, so kind of similar topic. Are you going to act pro-socially here versus are you going to act heroically? So this was the same people answering these questions versus answering these questions, and you can see it's a lot clearer a normal distribution here, which I feel very proud of. That was one of the intentions of creating this measure. So there were people who said, yes, I would still act heroically. Again, number 7 was the highest score versus 1 was the lowest score. So there were people who said, nope, absolutely would not do any heroic actions. Some people said, well, kind of, maybe, sometimes. And then there were people that said, yes, absolutely I would. So this is much more normally distributed. The mean was, I should have double checked right before this, 4.8 or something versus like 6 point something on the prosocial behavior. So prosocial behavior isn't a risk to the person versus a heroic behavior. It's going to be risky to the person acting. So not really any outliers. It makes sense versus here with the prosocial. Who are these people that said they wouldn't do anything prosocial ever? Are those outliers or is that real data? Well, I looked at their other responses. There were some responses in the data where they had to type out responses, and these were real people. They were just people who absolutely said they would not do anything pro-social. So I did not delete them. They're still in the data set because they were real, actual data. Even though it might look like outliers when comparing this data, and then got some bumps way over here. They were real people, real data, so I kept it in there. All right, so this is a histogram of ages in my sample. And so you see I had a lot more people who were in their 30s, so late 20s through their 30s, versus people that were in their 70s. I only had a few. So the mean here would be somewhere around, I forget what it was, but probably like 37 or something was probably the mean here. Standard deviation, it's pretty wide. It goes from 18 all the way, I think the oldest participant was 79. So a pretty wide standard deviation. You can see it's not very skewed, it's fairly normal, but these are just some practical examples to show you what central limit measures are and how we might look at them and look at the data relevant to them. So again, in tests and things for most of my classes in undergrad, you're not going to be doing this math unless I've told you otherwise. So let's jump to some other stats. Let's talk about what is a correlation. A correlation is probably one of the stats that you will find most commonly. Like in most of the papers you're reading, you'll probably read a lot of correlations. So correlation is a relationship between two variables. So we can look at a relationship between scoops of ice cream and happiness. If I give you 1 scoop of ice cream versus 2 scoops versus 3 scoops, is your happiness going to go up or down? So I would assume it's probably a strong positive correlation. So X might be number of ice cream scoops, Y might be happiness. So 1 scoop, 2 scoops, 3 scoops, 4 scoops. So for people who get 1 scoop of ice cream, they score about here on happiness. For people who get 2 scoops, they score about here on happiness. For people with 3 scoops, they get about this happy. For people with 4 scoops, they get about this happy. So that's what that means. It's saying these two relationships are related to one another. All right, so correlation is simply one variable's relationship with another. Let's look at another couple examples. In this case, happiness is probably causing, or the ice cream is probably causing the happiness, but correlation doesn't mean causation. You can have two variables be related, but not causing one another. So let's look at another one related to ice cream. In reality, there is a correlation between ice cream sales and pool drownings. So this is a real established fact that the more ice cream sold is related to more pool drownings. It's a positive correlation. So here's an example of these both up here are positive correlations. So this is a very strong positive correlation. This is still a pretty strong positive correlation, but not as strong as this one. This one's closer to a line. This one's not quite there's more variance around the line. So I can't really draw a line with my, I'm just looking at PDF here basically, so I can't actually draw a line right now. So what does this mean? What is causing this relationship? Are people eating ice cream and then drowning? No. It's that the fact is when you have days that are hotter, you tend to have more ice cream sold, and you also tend to have more people drowning in pools. So there is a cause that is separate. It's a third variable causing both of these variables. So you might have a day where there's, 300 ice creams sold or 500 ice creams sold. On the day when 300 ice creams are sold, maybe you have 7 people drowning. On days when there's 500 ice creams sold, you have 10 people drowning. So you see the drowning is on the x-axis here, so you've got it going up, and ice cream sales are also going up. But the cause is something separate. The ice cream sales are not causing the drownings. The drownings are not causing the ice cream sales. They are related to one another, though. So there's some relationship. You can see a statistical relationship, and in this case, there's a relationship with a third variable causing the both of them. You can also potentially have variables correlated that aren't related causally in any way at all. So let's look at the bystander effect of another one that is a relationship. So there is a negative correlation when we're talking about the bystander effect. When there's more people, there's less helping behavior. So let's say Y here is the number of people, X is helping behavior. So closer to the X, this is like 0 helping behaviors, this is like 10 helping behaviors. So this is 0 people there, 10 people there, okay? So with this, you've got Y is the number of people. So let's say you've got 10 people. When there's that many people, the helping behaviors are very low. People are not very likely to help. When there's no one there, people are a lot more likely to help. So the more people that are there, you get a diffusion of responsibility. And so this is an example of a correlation that might also be considered a causal relationship. But like we saw with the ice cream and pool, it doesn't mean, just having a correlation does not mean that it is a causal relationship. So let's look at another correlation that is not a causal relationship at all. So what we saw in the 1930s, so think about the 1930s historical events that might be happening around there. So we saw a negative correlation between weddings and men's suicides. So let's say Y is weddings. So when there was no weddings, there were more men's suicides on X. So no weddings, more men's suicides. Lots of weddings, very few men's suicides. So there was a negative correlation between these things. Researchers at the time made the claim that, well, the fact that men weren't getting married was causing suicides. It was not the case. So a couple of years later, researchers said, hey, this is a correlation, this is not a causal relationship. So write down in your notes, in the 1930s, what do you think might have explained both of these relationships? I'll let you pause for a second and think about it. So the third variable that was affecting both these relationships was the economy. This was the Great Depression, so there wasn't enough money for weddings, there was jobs being lost, homes being lost, things like that, and so with that, more suicides. So around the same times that there were more people losing jobs and not being able to afford weddings, there were also more people committing suicide. So there was a relationship here, a correlation, but it wasn't causal. The weddings were not causing the suicides were not causing the weddings. So a grim example, I definitely prefer talking about the ice cream and happiness example instead, but hopefully having multiple examples both of positive correlations and negative correlations makes it a little more clear the concept between what a correlation is. It's just a relationship between variables. There might possibly be a causal relationship, but not always, right? So correlation does not mean causation. In this example that we just went over about the weddings and suicides, it was not causally related to one another. So here are some actual real graphs of real data. So this was the intended heroic behavior scale, and this is the actual scatter plot of a graph with self-efficacy, a graph with moral courage, a graph with social responsibility, and a graph with empathy. So if you look at these are actual real numbers with real data plotted. You can see here that this line, the line of best fit, there's a lot of data packed right around that. It's a pretty clear line right here. So intended heroic behavior scale and moral courage scale were very highly correlated. Much more correlated than I expected them to be. This correlation was pretty strong at 0.79. So you don't have, this whole graph might look confusing, but basically in the middle it's showing what the measure was. And then so this box is intended heroic behavior scale and self-efficacy. So you can see it is a positive correlation, but you can see it's much more spread around the line than intended heroic behavior scale and moral courage. So 0.31, still a positive correlation, but pretty weak positive correlation, versus 0.79. The closer you get to 1, a correlation of 1.00 is literally just a straight line. So the closer you get to that, the stronger the correlation is. So we can say intended heroic behavior scale and social responsibility was 0.46. And then empathy was pretty similar with 0.40. All right, you can also look at empathy and social responsibility, pretty highly correlated, 0.63, and you can see there that the score here is the score on empathy, the score here is score on social responsibility. So for most people that scored high on social responsibility, they were also scoring high on empathy. Most people scoring lower on social responsibility were also scoring lower on empathy. So same with moral courage here. People who were scoring high on moral courage were also tending to score high on heroism. People scoring high on heroism were also tending to score high on moral courage, and low on heroism and low on moral courage. You can see this person here is a little bit of an outlier. They scored pretty high on moral courage here, but only about halfway up in heroism. So not an outlier. All of this data I went through clean, make sure sometimes when you do surveys online, you'll get people that literally take surveys with robots. So I got rid of all of the robots. So this is, I'm assuming this is all real people, and that's unless the robots are very convincing. But this gives you an example of, not like this, some actual real data, some actual real numbers to hopefully give you a better sense. Again, you're not going to have to do the math in my 2010 class, most of my undergrad classes, but hopefully this makes it a little more clear and you can see what a 0.31 correlation, this one, versus a 0.79 correlation looks like. All right, so and one way that we do a lot of our work, especially when looking at treatments versus controls, is by comparing means. So we often do this in an experimental setting. One group will get the treatment, the other group will not get the treatment. We'll test them on heroism or pro-social behavior, purpose in life, happiness, depression. We'll test whatever outcome measure and we'll see if the two groups are actually different. If we were supposed to treat depression, their depression score should be lower, right? So our treatment group should have a lower score, a lower mean score. So you can really compare any groups. So you can compare on sex, like male and female. You compare on age, so 18-year-olds versus 30-year-olds. You can have multiple groups. So let's say we're prepping for an exam. I have one group study for 10 hours, or I force them to study for 10 hours. I force another group to study for 5 hours, and I force another group to study for 1 hour. I can compare, what are your scores? What's the average score for the 10-hour study group? Hopefully it's pretty high with 10 hours of studying. What's the average score for the 5-hour study group? What's the average score for the 1-hour study group? And I can compare those average scores. So if you had a control group with a mean of 5 out of 10, so let's say your whole scale, the happiness measure, whatever it was, went to 10, and the control group gets a 5 out of 10, and the experimental group gets a 9 out of 10. Does this mean the experiment worked? Maybe, but really you need to know more here. You need to know a little bit more about these groups. So that's what we do with comparing means. Things like independent samples t-test is one statistic we use to compare those means. Because yes, it matters how far apart the means are, but it also matters how much data is under these arches. It matters how wide the data is spread. It matters how much overlap there is. It matters how many people are in each sample. And so these kind of statistical tests take that all into account. So are these means statistically significantly different? So maybe this is our control group in blue and our treatment group in red. Maybe we're trying to make people more happy or something like that. So is this difference here enough to say that it worked? Well, you need to know more things. Standard deviation, so how wide this is, how skewed it is, what's the sample size? If this group here was a sample of 10 and this group here was a sample of 10, I would not put much stock in this replicating in a general population. If this was a group of 2 million people and the red group was 2 million people, I would say there probably is some difference here. That's probably a real difference. Now, is that difference dramatic enough that you want to pursue this treatment? Well, it really depends on what it is. If this is people making $2 more a day versus $2,000 a day, well, one is going to be, one of those might matter, one of them might not. It depends on the sample too. In some places, $2 might be a really big difference. In other places, $2 might not be a big difference. So if there's too much overlap, if the sample sizes are small, this difference might not matter. So that's one reason we use things like box plots. We can use these box plots to show this same kind of data in a slightly different way. So this line in the going straight up is the mean for each group. Here in this box plot, this little diamond is the mean. But then you can also mark the median with this line, or sometimes one is the median and the other is the mean. I didn't actually put the guide of which one is which in this specific case. And then you can have a first standard deviation here. And that gives you a lot more data about the spread. And then this green part is the 95% confidence interval. So this is our data. We have our control group, we have our experimental group. We are pretty sure, we're about 95% confident that based on this whole spread of data in our sample, that the true population difference will fall in here. And that's what the 95% confidence interval means. We're about 95%, or we're pretty confident that this is where the actual population difference will fall. So we can see here they're not quite overlapping, so that shows a good thing. We're probably having a real difference. Our treatment to make people happier looks like it worked. So that is one way to look at this data. That gives you a little more information. But the main point here is you're comparing the average scores of one group compared to the other group. So another way to look at this is literally a stats printout. I had people in my dissertation who had been awarded or recognized for heroic acts, and then people who had not, and I compared them on the scores. So up here, group 1, there were 582 of them. So that's the sample size of that group. Their mean was 4.36. So the average of people who didn't do heroism, they scored about a 4.36 on my measure of heroic behavior. Here's their standard deviation. You can see the standard deviations are pretty close to one another. And this group is 109 people. So there were 109 heroes in the group. They scored a 5.45. So 4.3 versus 5.4. That is the mean difference. So I did a 2-sample t-test, and I got a t-value, which is essentially just a little bit the stat to compare, is this difference matter, and it gives me a p-value. So the probability that I would get this result, if it was actually chance, is very small. Again, this hopefully giving a little bit more of the backgrounds of the numbers, especially for those of you who have been in a stats class. You might recognize these and say, oh, okay, I understand this. For those of you who haven't taken a stats class, hopefully this helps understand and doesn't make you more confused or worried, because you're not going to be calculating these. So this is the 95% confidence interval for this result. The true difference between these two groups, or the true value of the t between these two groups, is somewhere between 1.3 and 0.8. So it's probably a real difference between the groups, is essentially what that's saying. So there's not too much overlap between these two groups. There is some, obviously, with these means and standard deviation, but these groups are pretty far away from each other. It was pretty clear that it was assessing heroes and non-heroes as different groups. So that is comparing means. So essentially these numbers are related to what you would see in a graph like this. All right, another thing we do in stats a lot for psychology is multiple regression. This is really nice because it lets you look at multiple correlations within and how they relate to one another. Do they have an impact's the wrong word because that suggests causation. Multiple regression looks at the relationship between lots of variables at the same time. So we might be looking at a variable like oxygen and how much oxygen you're taking in. Well, your gender might matter, your heart rate might matter, your weight might matter, your age might matter. So we look at all of them together in a multiple regression and see which ones matter the most. So it seems like, just looking at these stats right here, age mattered the least. These other variables had a bigger impact. So, and you can also with multiple regression say, does weight have an impact? Again, probably not the right word because that suggests causation. So does weight, heart rate, or gender have any relationship with or apart from any other variable? So weight and heart rate, do they have a relationship together with oxygen consumption? Or do they have relationships by themselves, even when you pull out the data that we can find about heart rate? Things like that. Knowing all these variables and how all of them are interacting with each other, so multiple variables interacting with multiple variables, if you know all that, you might be able to predict the outcome better. So if this is a diet or oxygen consumption or like weight loss or happiness, the more of these variables that you know, and knowing how they're related to one another can help you be more accurate in your predictions. So that's what multiple regression is for. Knowing more of these relationships let you predict any kind of outcome better. Lots of colleges use multiple regression as an admission tool. So they'll take your GPA. They'll take they literally have a number to say if you have 1 versus 2 parents who have gone to college, how far they went in college, they will get given some kind of score. So what's your high school GPA? Did your parents go to college? What are some of the other things? SAT or ACT. They factor these variables in together to predict what will be your GPA at the end of your freshman year. That's what most of the schools do to determine the cutoff for people they will admit or not admit. And they will have a cutoff. They'll say, all right, if we are pretty sure, based on this regression model, based on these equations and how we know these variables interact, we're pretty sure you're going to have a GPA above 2.5, you can come in. We'll admit you. Some schools might say it has to be above a 3 or even a 3.5 or something like that. So they will calculate that and then reject or accept students based on that. So and they're using multiple regression. Now again, this goes back to measurement tools. SAT and ACT are absolutely terrible measures of how you will do in a college setting. We know that now. We know there's a lot better ways to predict that, but a lot of schools are still using those. So that goes to, in psych, we need better tools. Making better tools makes for better predictions. If you're trying to predict an earthquake, you're using multiple regression. How long ago was the previous earthquake? How many fault lines are in this area? How much activity has there been recently? What kind of rock is it? These are kinds of variables that I'm aware of that goes into a multiple regression equation to predict how likely it is for an earthquake to happen or not. So hopefully these examples help the concept make sense. Again, you're not going to need to calculate this in most of my undergrad classes, but hopefully you understand the concept as you read about it and you're reading about this is predictive of this, those kinds of things. So multiple regression is like correlation with multiple correlations at the same time. All right, and mediation and moderation are different ways to look at how variables interact too. So mediation, the model is kind of like this versus moderation is like this. Mediation can explain how variables are related. Sleep quality might be affected. So here, let's look at mediation. Sleep quality X. Effect might not be the best word here because, again, it might not be causal. And then Y is academic achievement. But the mediating variable here might be alertness. What if you get 10 hours of sleep, but you're not alert? You're not actually paying attention. You're paying more attention to the text you got from the person you're wanting to take out on a first date. If you're not alert, your academic achievement might not be as high. So it's a third variable that might be affecting this in a specific way, because we might expect sleep quality will be related to academic achievement, but there can be mediating variables. So full or partial mediation, depending on what you're talking about, this mediator might completely eliminate this direct relationship, and it might only go this way. So that's what you've got to do studies for. You've got to see if this relationship exists in this way, if there's mediators, if there's moderators. So we'll get to moderators now. Moderators are a little bit different, and they're affecting the strength or direction of relationships. So let's look at another example. Maybe this variable here is mental health. Again, we're talking about sleep quality, academic achievement. Maybe mental health makes it so the relationship goes back and forth. So if you have good or bad mental health, your academic achievement maybe impacts your sleep quality more than your sleep quality impacts your academic achievement. So it affects or moderates this. So maybe there usually is an impact between sleep quality and academic achievement, but if your mental health is good or bad, maybe that relationship is less or stronger. So this is just different ways to talk about and discuss how variables are related to each other. So a variable is really anything that can vary. Height is a variable. My height is different than my children's heights and different than all the students' heights. There may be students who are exactly the same height as me, but everybody has a variance, a variable of their height. Weight is a variable. How you would score on a happiness measure is a variable. What you would score on a pro-social behavior scale or survey is a variable. So we look at these variables and try to answer questions around the world. So what's your score on the first exam? That is a variable. How much sleep did you get before the first exam? That's a variable. These are all things that could possibly vary. So with this, mediation, moderation, they can work together in a mediating and moderating relationship. So again, we're getting more complex here, more variables impacting things. So we have statistical models to account for these things, to examine them, to investigate them, to figure out how do things work together. So we've already seen this example in previous classes of the theory of planned behavior. So you can see here mediating and moderating. Right? So the moderation here of an actual behavioral control, you might intend to do something, but if you actually cannot do that thing, it's completely moderated and it's only affected by this, even if your intention is really high. So again, you don't need to be worried about doing the math on these things. Hopefully you have a better understanding of correlations after this discussion. Hopefully you have a better understanding of comparing means after this discussion. You understand multiple regression a little bit more, and you know the difference between a sample and a population, and then why we try to infer from a sample relevant to a population. So those are some of the core concepts in stats relevant to psychology that I hope you take with you as you're reading research, as we're talking about examples in class, and hopefully this didn't confuse you more as you're going into reading. Hopefully it makes a little bit more sense. Feel free to watch over this again before the exam as well, because these concepts will be on the exam, even though you're not going to have to do the stats to calculate a correlation. As I'm recording this, I can't remember if I have any questions about like specific numbers related to correlations, kind of about this. So stronger correlations closer to 1.00 or even negative 1.00. So a negative correlation, this would be like a negative 0.73 versus this is a positive 0.73. So the negative just means that's the direction of the relationship. All right. Well, hopefully that's helpful as you read your papers and learn a lot more about real research and the stats that we are learning in the field of psychology.